So I'm going to start by asking questions there. I think somebody in the class is developing mobile health device. So this is the body. This is the body. Okay, and this person has two arms, two legs, and he has a heart right here. His heart is here. Now he wants to measure electrocardiogram on the watch. Okay. So he's going to develop a watch where he wants to measure electrocardiogram. Since everything available to him is just a watch, he wants to put electrode right here. So you're going to measure electrocardiogram, you have to measure voltage difference between 2 points. So you have to have at least 2 electrodes, right? So he installed 2 electrodes like this, under the watch. And inside the watch, there's going to be lead wire and ECG amplifier and A to D converter, and he's trying to display ECG signal and detect heart rate and so on. So what's the problem here? Do you think he's going to be able to detect ECG or not? No. Why not? Why not? So he's not going to get any signal in this case. Okay? Then what about this configuration? What about this configuration? Is he going to get any ECG signal or not? We have to know where is the heart. Okay? We have heart here. Okay? We have heart. So you should be able to answer why, in both cases, it's going to be very difficult to detect any ECG. And why? Okay? You have to explain this using read field theory. Anybody?
Sir,
Yeah.
Whatever device we use for measuring ECG or something, we need some voltage difference. So from these 2 configurations, we didn't see how we take voltage difference. From one vein or in one line or.
Well, actually we need one ground electrode somewhere, but that's not relevant here. So I just intentionally ignored the reference electrode. So let's assume there's another electrode for voltage reference, okay? Ground electrode. So what we can do is we have 2 electrodes like this, right? And then we can construct ECG amplifier. Yeah? With a gain of 1000 and bandwidth of this much. Yeah? And then we can have ADC and micron, yeah? And then LCD. Yeah? So people can not easily, but you can develop this kind of instrument, yeah? In a form of watch or whatever. And this point is connected to here, and this point is connected to here. And in that case, to those the electrode. Yes? There must be, well, not must, but it's going to be better to have a third electrode as a voltage reference electrode. Yes?
Okay, these 2 points must measure some voltage. Okay?
Yes.
So if we draw like this is like, let me think, if we insert some current from
Yes.
this point, so it depends on the direction of lead vector. Like,
Yes.
So it every configuration will have different direction. Like if we think about first one, like
Yeah.
in this, so the direction of current is like this, like down.
Yeah.
But here the direction is going towards the heart. So maybe the signal is different.
Yes. The signals are different for this case and this case. My comment was in both cases, it's going to be very difficult to measure any ECG signal. You are not going to measure ECG signal. Why? I think the way you try to
Yeah.
explain, that's correct. Yeah? So we have to explain this based on lead field. So what kind of lead field we are going to have for each case. So to find the lead field, what should we do?
Means
We need to inject current.
yeah.
Yeah? We have to inject current. So let's do imaginary experiment.
Yeah.
So we are injecting current from here to here. Yeah? Then current enter into the body, and how they will flow. Most of the current will flow like this. Yeah?
But in this case, 2 point is one is source and one is sink,
Yes.
right?
Yes. Sure. So we should do already in this way. After this, I'm going to review the lead field theory again, yeah? Because we have to repeat several times to make sure everybody understands that. Yeah? But this is going to be something to stimulate your thinking. Yeah? So, in order to find out lead field, we inject current between the pair of electrodes where we are going to measure voltage. Okay? So we are going to measure voltage between these two. So in order to find out lead field, which is sensitivity map, we have to inject current. Yeah? So we are looking into the body through these 2 electrodes. So how do we look into the body? If I ask you to look into a box, then you make a hole and then you really see what's inside, right? Here we are talking about measuring voltage. Yeah? So how do we see the body where we are going to measure voltage? We inject current. That's the way we see the body when we measure voltage from the body. Okay? Can you see the heart from here? What I mean by see the heart,
The value.
is there any current reaching the heart? We are injecting current here. Okay? If this injected current flow through the heart, then we are seeing the heart.
Yeah.
Yeah? How much current will flow here? If we inject current between these two, then how much current will be flowing all the way?
0.
So how much current will it be? Almost zero. Almost zero. Okay? So this pair of electrodes cannot see the heart. So even though there's very strong dipole, which means very strong current source from the heart, the heart is beating. So there's going to be very strong dipole moment at the heart. The signal you measure here, that's going to be voltage, is, what is this? lead field vector, lead vector. And what is this?
Moment.
Dipole moment. Yeah. This lead field vector is going to be the amount of current density flowing through this point when we inject current between these two vectors, right? Based on the reciprocity theorem. Yeah. Then if we inject current between these two, this lead field vector, this C vector, is going to be almost 0. So the measured voltage here is going to be almost 0. Okay?
But nowadays we have some watch measuring.
They don't measure ECG. Do you know how they measure ECG using watch?
Another device.
They measure pulse rate not by ECG but by using
Precision.
pulse oximetry, using light. Yeah? So they are not using ECG to measure heart rate because they attach just 2 electrodes here. It's not possible to measure ECG. But some watch measures ECG. How they measure? Underneath the watch, there's one electrode. So that one electrode is touching this part. Yeah? And on the top surface of the watch, there's another electrode. So you have to touch that one using the other finger. So what's the configuration? In that case, after this arm is too short. Yeah? After here's one electrode, underneath the watch, and here's another electrode because you touched top of the watch using the other hand. So we have this kind of electrode configuration. Then where's the heart? Here's the heart. What's going to be the lead field? We inject current from here to here. Right? So current must flow from here to here. So this current must go through the heart. Yeah? So we have strong lead feedback. Okay? So we have a signal. Yeah? In this case, you have ECG signal. But in this case, you don't have ECG signal because you cannot see the heart using this pair of electrons. Okay? So what's going to be happening in this case? The current will flow this way. Yeah?
Not rich.
This way. So there's going to be a little bit of current flowing in this way. But there's going to be almost zero current passing through the heart because that's going to be too far. Yeah? So it's not possible to measure ECG in this configuration or in this configuration. So when you measure ECG signal, you have to have 2 electrodes. When you inject current between those 2 electrodes, the injected current must pass through the heart. Yeah? Otherwise, that pair of electrodes cannot measure or cannot see the dipole inside of it. Yes.
So if we apply just 2 electrodes above the heart and down, like here and here.
Oh yeah?
So
Instead of this configuration, you can have, so here's the heart, So if we attach 1 electrode here and 1 electrode here, can you measure the ECG signal? Think about it. We inject current. This is the source, and all the current we injected here must exit from here. So current must enter the body here and pass through the body and exit here. So there's going to be quite a lot of current flow through the heart. So we have a strong enough lead vector.
only 2 electrodes is enough to measure the ECG signal? Because
Yes, yes.
they measure many.
In order to measure voltage, you just need two
Yeah.
electrode or two probe all the time. Yeah? Because voltage is basically voltage difference. Yeah? The reason why they use 3 electrode at least is because this, for the instrumentation purpose, it's better to make this amplifier as a differential amplifier rather than single-ended input amplifier. So they use 2 floating electrode and 1 grounded electrode. So body is connected to the circuit ground using the third electrode, and these 2 electrodes are used for the ECG measurement. So this is a differential voltage measurement. If we want to single-ended voltage measurement, then you can just do this. Yeah? Then you can just measure ECG using the 2 electrodes. Yeah? But in this case, you have more noise. Yeah? You have a higher noise for instrumentation reason, for circuit design reason. So in this case, lead vector through the heart is along this direction, right? Because current is passing horizontally. Agree? I don't like this. And so we have a horizontal lead vector for this kind of electrode configuration. Okay. And in this case, we have vertical lead vector. Right? Okay? Yeah. Now we are measuring ECG using these 2 electrodes as 1 channel, first channel. And we are measuring this ECG as a second channel. So we are displaying ECG in 2 channels. The waveforms are going to be same or different? Same or different?
Amplitude is different. Right.
At certain time, this heart and this heart, they are the same heart, right? This is a single person. Yeah? We have 1 electrode pair between these 2 and second electrode pair between these 2, the same heart. From the same heart, at certain moment, there's going to be 1 dipole moment, equivalent dipole moment. Okay? During 1 cardiac cycle, that dipole moment happened to be this at certain point of time. Then this voltage is going to be large or small? Large. Because you need to calculate inner product between this vector and this dipole moment vector, right? So this lead will produce big signal. Okay? But at the same time, this channel is going to give you voltage value of 0. Okay? Cardiac beta change with the time. Okay? So at certain time moment, this electrode pair and this electrode pair will give you different signal. This electrode pair give you the information about the vertical component of equivalent dipole. Okay? And this thing will give you the information about horizontal component of the dipole. If you measure both of them, and if cardiac vector, this equivalent dipole, is a 2-dimensional vector, okay, then using just these 2 lead or 2 pairs of electrode, you fully express what? You can fully express the equivalent dipole. Okay? But dipole moment from the heart is 3-dimensional vector. Okay? So you need 1 more lead. So how do you attach this lead? So you have a horizontal component, you have vertical component. So you need depth information. So how should you attach electrode? 1 electrode here, another electrode at the back. Okay? That's called XYZ lead. XYZ lead. XYZ lead. Yeah? In ECG measurement. So if you measure ECG using 2 electrodes in this configuration, second pair of electrodes are on this configuration, and third pair of electrodes between this configuration, one here and another there. Then, by measuring 3 channels of ECG signal, and for every instant, you have 3 values, right? Those 3 values will give you one vector, 3-dimensional vector, right? And as time goes by, this magnitude and direction of that vector will change. Yeah? Then you are displaying cardiac vector as a function of time. Yeah? That's called vector cardiac. Vector cardiac. So you can use XYZ lead to display vector cardiac, which is the display, 3-dimensional display of equivalent dipole moment of your heart, which has also a lot of diagnostic information. Yeah. Make sense? Okay, I'm going to repeat. So whenever you try to measure biopotential, you have to locate where is the source. Source is the what? Equivalent dipole moment. It could be the heart, muscle, or brain, or whatever. Okay? Wherever you have neurons, okay, which produce action potential to contract muscle or to do some thinking or to sense something or to hear something, whatever, those neurons are going to produce current. Okay? And that current is expressed as equivalent dipole moment. That's the source. That's the signal source. Okay? And when we measure voltage produced by this equivalent dipole source, we have to use at least one pair of electrons attached somewhere. Yeah? Okay. So we can attach electrode here or there, whatever. Okay? By attaching electrode, what we are doing is we are trying to see the equivalent dipole moment, right? So here, what's the meaning of seeing? The meaning of seeing is to inject current between those 2 electrodes and try to send or reach the dipole moment through the injected current. So you are sending current, yeah, between electrodes. And if the current you inject it appear here, yeah, with a significant large magnitude, then you can detect the equivalent dipole. Otherwise, you're not seeing the dipole moment, so there is no signal. Okay? Okay. So now you have a dipole in the brain. So where should you attach electrode to measure EEG? Around here. You know, you're measuring EEG and then you attach electrode down here. What are you doing? Yes, no, you don't see the brain. Okay? So it's not just location, but also you have to think about distance. Yeah? You know, this electrode and this electrode, they are separated quite far. Right? From here and here. It's very far. The distance between those electrodes is very far. But it's okay. Why? All the current from here will pass through the heart. Anyway, yeah? The second question is, this is the first case. Second case is something like this. They are too far. We'd like to see the heart at closer distance. So somebody suggested putting electrode here. Is there going to be much advantage? Think about it. in terms of signal sensitivity, is there going to be much advantage? There is advantage, okay? Which is different region for different region. But in terms of the sensitivity or read vector, is there going to be any advantage? So you inject 1 ampere, 1 milliampere here, yeah? And minus 1 milliampere, source sink. 1 milliampere here, minus 1 milliampere here. And this is the current density. And there should be some current density here. Which current density is going to be bigger? I would say almost
Same.
same. Why?
Because it's the same area and
Because this cross-sectional area is same, yeah? And you are injecting current here. You inject current here. All 1 milliampere will pass through the arm and spread, and then convert to the other arm, right? Here, all the current will just spread and then convert to the other electron. So they spread almost same way.
but if we the body is grounded somewhere, so this will be different.
Doesn't matter. Think about it. Think about it. Choice of ground electrode is really relevant. It doesn't matter. It doesn't matter where you put the third ground electrode.
But the path of current will be
So when you inject 1 milliampere here and minus 1 milliampere here, and you have a ground electrode, is there going to be any current passing through the ground electrode? No, no, no. This is not for current sink. This is only for reference, voltage reference. Okay? This is nothing to do with the current injection. Okay? Okay. So this electrode configuration and this electrode configuration, they are the same in terms of ECG measurement. But this one has a little more advantage. What is that advantage? So people attach electrode here and here, or sometimes here and here, when they measure ECG from a person who are learning. Okay? If the patient moves a lot, then usually he moves on. Okay? It's very difficult to move this part. So when people move, there's going to be change in contact impedance that's going to produce motion artifact. Okay? So that motion artifact has nothing to do with the ECG signal itself. Okay? So this position is better to reduce motion artifact because this trunk doesn't move much compared with the arm. But other than that, you know, the ECG signal amplitudes, they are almost same.
ECG, they use the 3 electrodes, right? For ECG signal. Most of the devices
It
they
depends.
use 3 electrodes.
They can use 3 electrodes. Not all the time, but they can use 3 electrodes. Yes.
But I didn't see before that this electrode
But that's not very standard procedure. The most widely used ECG electrode positions are left hand, right hand, left leg, right leg, 4 electrodes. And using those 4 electrodes, they produce 6 signals. Okay? And then they attach V1, V2, V3, V4, V5, V6. 6 electrodes on the chest. And using those, they produce another 6 ECG signals. So including 6 frontal plane ECG signals and 6 precordial ECG signals, they produce 12 ECG signals. That's standard. For clinical diagnostic ECG. For the monitoring purpose, for the monitoring of your heart beating, they just use 3 electrodes. One here, second one here, and the third one, which is for ground, anywhere in the body. anywhere. Doesn't matter. Okay? In that case, they are just measuring ECG signal between these two points. Okay? Yeah. Any question? So this is something you have to test yourself to find out whether you understood the read field theory or not. Okay? Okay. Now let's think about impedance measurement case. So the people who are working on mobile health device, they try to measure heart rate. They try to measure heart rate on a band or watch. Yeah? So they quickly realize that if they attach two electrodes here or in any direction, they are not measuring any ECG signal. Yeah? Because of this. Yeah? Unless you have a really high gain, ultra low noise amplifier. Okay? Unless you have very good amplifier, it's hopeless. Yeah? So don't even think about it. It's impossible. Okay? Yeah. So people are using LED to transmit light to the blood vessel and use a photodiode to detect reflected light. Okay? And that method is called photoplasmography. So they are detecting change of blood volume through the blood vessel. And that technique can be used to detect saturation on top if they use multiple wavelengths of the light. Okay? But that technique also has some difficulty with contact and ambient light noise interference and so on. So some people try to measure impedance on the wrist. So let's think about that, if that's possible or not. So now let's just think about hand. So inside the hand, there must be blood vessel. There must be blood vessel, right? Agree?
Yeah.
Everybody has a blood vessel. And when the heart contracts, it's sending blood from the left ventricle to where? To the artery, aorta, the largest artery, right after the ventricle. And then that blood spread all over, right? So when blood is pumped from the heart through the artery, we are going to have something like this. It will be much better if I can do animation here, but at one time you are going to have this kind of blood, and a little bit later that will appear probably here, after some time, and after some time later that will arrive here, right? So this is blood. So this kind of blood is passing through from here to here and spread all over and then return, right? So when we have this much of blood here, blood has a lot of ions, so its conductivity is high. So the electrical impedance between these two points is going to be bigger, smaller, when we have blood passing through. Compare with this kind of setting. The impedance between this around this segment is going to be large in this case, and when blood is appearing here, the impedance around this segment is going to be reduced because there's going to be more conductive fluid in that region. So we want to measure the impedance of this body segment, right? This body segment. What should be the electrode configuration? So what should be the electrode configuration?
Up, down.
Well, so this is the hand. Yeah? What about this kind of electrode configuration? Which we can easily attach underneath watch or band. Is it good? To measure impedance, we have to inject current and measure voltage, right? So far here, ECG, EEG, all of those cases, there exists internal current source, which is the current source produced by neurons. Yeah? Neurons. So ECG measurement, EEG measurement, for all of those biopotential measurement cases, we are dealing with the internal current source. Yeah? Internal current source is mean neurons. Yeah? But when we measure impedance, impedance is a passive property, passive material property. To measure passive material property, what should we do? We have to inject current. Okay? And measure the voltage induced by injected current. Okay? So injection current is going to be equivalent to the internal current source when you think about lead field theory in this case. Okay? And voltage measurement is going to be the same. Right? Okay. So let's think about lead field in this case. I'm going to inject current between these two, and I'm going to measure voltage between these two. So what's going to be the lead field? So when we measure biopotential or bioimpedance, if you are going to find the lead field, forget about current first. Yeah? Current, you forget about current. Yeah? Current injection is going to be equivalent to what? Internal current source. Yeah? So let's forget about current injection. Yeah? Now let's think about voltage measurement only. Yeah? So forget about this thing. So what's going to be the lead field using these two electrodes? It's going to be something like this. I'm going to draw the cross section of the wrist. Yeah? And here's going to be blood vessel. Yeah? And the diameter of the blood vessel is going to be expanded and shrink, right? Okay. Now, I attach the 4 electrode like this, and I'm injecting current, and I'm measuring voltage here. So what's going to be the lead field here? Lead field, to find the lead field, what should we do?
Inject.
We have to inject current where?
Measure.
Between this voltage measuring electrode. Okay, don't forget this. Don't forget this. So we are injecting current here. This is imaginary thing. Yeah? Yeah. Okay, so we inject current like this. So there's going to be some current, yeah, passing through here, right? And then what's going to be the voltage measured between these two electrode pair when we injected current?
Inner product.
So now we know what's going to be the lead vector. Around this point there's going to be lead vector. So these are C vectors, right? The voltage is going to be sum of C vector inner product between C vector and the current density vector. Right? So inside the wrist there is no endogenous or spontaneous regenerated internal current source. Yeah? The current is produced by the injection current. Okay? So now we have to think about what kind of P, current dipole distribution, is going to be there by the injection current. So we are going to have this kind of injection current. Yeah? This kind of injection current. So the signal, measured signal, is going to be inner product between red vector and blue vector. Okay? Is it good or bad?
Good. strong thing.
Is it okay? This is okay. Okay? Now I'm going to give you a second example. And some engineer didn't like it. Okay? He didn't like it. So he proposed to inject current using these two electrodes. Which is good. This is just a bang. Okay? So he's injecting current like this. And he's suggesting to use these two electrodes to measure voltage. Yeah. Yeah. To have very stable four contacts all over the band. Makes sense? Looks like a good idea. Yeah?
Signal is 0.
Is it good or bad?
Signal.
So let's go into the lead field. To find the lead field, we have to inject current where? Using this degree. Right? So this is going to be lead field. This is going to be lead field. And here we have a broad vessel. Okay? And what's going to be the current density produced by the injected current? You know, this thing. Yeah? This thing. So we have to calculate the inner product between red vector and blue vector. What's going to be the value? Almost 0. So is it good or bad?
Bad.
This is bad. This is bad. Yeah? This is bad. You know, even though this blood vessel increase or decrease due to change in blood volume from the beating heart, the measured voltage is going to be very small because lead field vector and current density vector are perpendicular. Yeah? So it's not a good idea to use that kind of electrode.
But still we have some difference when we
Yeah,
inject
there's
the
going
blood.
to be some difference.
So
Yeah.
they like to measure like the difference in to calculate the pulse.
The signal itself is too small.
Yeah.
Yeah. Signal itself is too small. What about this configuration? 2 electrodes here and 2 electrodes here. Yeah? And you inject current here and you measure voltage here. Is it good or bad?
Good.
Think about it. Think again. So what's going to be the lead field? Draw it. What's going to? This is going to be the lead. Yeah? And here you have a blood vessel down here. Okay? And this thing is changing. Yeah? And what's going to be the current density field? This thing. Yeah? Right? Okay. Now, around here, they are in the same direction. Yeah? Blue vector, red vector, they are in the same direction, right? So it looks good. Looks good. But the magnitude of these blue vector and red vector, they are going to be small compared with the current density here. Agree? So there's going to be a lot more current passing through here in the region near the electrode, and there's going to be much less current passing through here. Yeah? So this blue vector and this red vector, they are in the same direction, but the magnitude are small.
So what's the difference between the first configuration?
Similar.
Yeah.
I didn't say this is the best one. And what other problem we have here? What other problem? Look very carefully. There's some other problem. if I check this point, okay, this point, how come I don't have okay, and if I choose this point, I have red vector pointing in this direction. I have blue vector pointing in this direction. Okay? They are in more or less same direction, and the angle is less than 90 degrees. Okay, so when we calculate inner product, the inner product is going to be positive value. Agree? Now I choose this point, or any point a little bit above there or down here. I have blue vector in this direction and red vector in this direction. Their angle is bigger than 90 degrees. The inner product between these two vectors is going to be negative. But if this person has a very large blood vessel, actually, I didn't choose where. Let's say I chose somewhere here where we have negative value, yeah? And blood vessel is increasing, which means the conductivity there increased. Yeah? If conductivity increased, then we should expect smaller voltage, right? If sensitivity is positive. Yeah? If sensitivity is negative, then the conductivity increased there, then the voltage increased. The voltage changes in the opposite direction depending on the polarity of sensitivity. Okay? So there's going to be confusion in this case because we have positive sensitivity and negative sensitivity. Yeah? So we don't know whether blood vessel is increased or decreased. Yeah? There's going to be confusion. Yeah? So what's going to be the best position or best electrode configuration for this kind of case? This is no good. Yeah? This is no good. Yeah? This seems to be good. Yeah? Seems to be good. Yeah? So what should be the best one? Okay.
Barrel.
You can answer that next week in Vito. Okay. Interesting problem, right? Yeah?
But what in midterm?
You can think about it from today to next week. Yeah? You can come up with a good answer. Yeah?
Can we check the answer now?
No, think about it. Think about it. Yeah? So, I'm talking about all of these because the things you learned so far, those are not just mathematics. Those are really, really practical knowledge. So if you don't understand lead vector and lead field, there is no way you understand why certain electrical configuration is giving you big signal and why other electrical configuration give you almost no signal. It's going to be very mysterious. Yeah? But there is nothing mysterious in this bioelectromagnetism or biomedical engineering. Everything should be explained. Okay? So any questions so far? Yeah. So from the knowledge of lead field theory, you should be able to design electrical configuration for all different kind of biopotential measurement. ECG, EEG, EMG, EOG, whatever. What should you know? you should know where is the current source, internal current source, produced by neuronal activity, and what's the direction, its magnitude of that equivalent dipole moment, yeah? In the heart, in the brain, or whatever. Okay? So you know the signal, or you can estimate the signal, then you have to choose electrode position. Then what should you do? You should inject current, yeah, through those two electrodes where you are going to measure voltage, and then produce the map of lead field. Yeah? And then there's going to be lead field vector passing through that current source. If the inner product between lead field vector and the equivalent dipole of the source has a similar direction and large amplitude, then that's going to be the best electrode configuration to detect or measure that internal neuronal source current through the voltage on the surface. Okay. When you are doing impedance measurement, on the other hand, yeah, when you are doing impedance measurement like this, you can use exactly same theory. Okay? You can just replace internal equivalent dipole by the current source, current density produced by injected current. Lead field produced by injecting current between voltage measuring electrode, that's going to be exactly same. Okay? Did I confuse you? Are you okay, Hassan? Now, this is very simple message, but I know some of you are not still. I'm not sure. Some of you are not sure about it. So I spent almost more than half of the semester to teach you just this. But that's the essence of bioelectricity. That's really the essence of bioelectricity. The rest of the theory, those are related things. Yes?
How do we ground it?
How do you ground it?
Yeah, if you have erased it.
Okay. You know, I know why you ask this question. Yeah. I studied electronic engineering for my bachelor program, and I couldn't understand the concept of ground.
No, I mean if we make a product, how can we ground
Yeah.
erase it?
Okay. Maybe you asked a different question, but I want, because you asked this,
Yeah.
I want to talk about something related to that, and I come back to your question. So this is the body. This is the body. This is the body. It's just my body. I'm standing in. Am I grounded? Am I grounded?
Yes, I mean the condition.
I'm not grounded. I'm not grounded. What's the meaning of grounded? So there's term of ground. Yeah? Ground. What is ground? Some people say earth. Yeah? Probably heard about the term earth in circuit theory. Ground, earth, what are they? They are really ground out there. And what is the earth? This is really the earth we live. Now what is the earth? This is the earth. This is the moon. Here's the sun. You know, this earth is really that earth. Yeah? Ground means really the ground out there. Okay? Am I grounded now?
Yeah.
When you say something is grounded in circuit or something is connected to the earth in circuit, that means this body is connected through a conducting cable to the ground or to the earth. Am I grounded?
But the body is.
You're all
Am I grounded?
Yes.
Why I'm grounded? Is this conductor? Is this conductor? This is not a conductor. This is an insulator. This flow is insulated. So if you say I'm grounded now, in order to not to be grounded, I have to do this, right? I'm not grounded now. You're not grounded now.
So if now I'm not grounded, so if I touch the electricity, so no current will through.
Very good question. Yeah? Very good question. So this is a body, yeah? And this is not grounded. So this is a you asked something which triggered some other thing.
Yeah.
This is a good question. So who's generating electricity?
Electrons.
Yeah.
Movement elect-
Power plant. So who's generating electricity? Power plant is generating electricity. Yeah? So here's the power plant. Here's the power plant. And power plant was constructed on the earth. Okay? So this power plant is located on the ground. Okay? Agree?
Okay.
This body is floated from the ground because I'm not touching it here. Yeah? If I remove my shoes, if I remove my socks, and if I stand on the sand out there, then am I grounded or not? I'm grounded. Yeah? I'm grounded. If I do that, then I'm grounded. If I bring metal stick, conducting stick, yeah, and go outside, and I push the ground using the conducting stick and holding the stick, then am I grounded or not?
Yes.
Then I'm grounded. I'm grounded. I'm grounded in that case. If I touch this metal chassis, am I grounded or not? I'm almost grounded. Because this conducting material is connected to concrete where we have some conductivity, yeah? And also there's some metal there, and those are connected to the ground through the building structure. So I'm somewhat grounded in this case, not fully, but somewhat connected to the ground. Yeah? If I touch metal chassis, which is used here, yeah, then I'm somewhat grounded, but not fully grounded. Yeah? The resistance between my body and this ground is not zero. It will have 100 ohm, 100 kilo ohm or some value. Yeah? But if I'm standing here, I stand here, and you bring me multimeter, yeah? And I'm holding one side of the multimeter, and I put the other side of the multimeter to the ground. Then what's going to be the resistance between me, my body, and the ground? Infinity. It's open, so I'm not grounded. Okay? So grounding means physically connecting object to the ground. Really to the ground. That's grounding. Okay? That's real meaning of grounding. So what's happening here is he is sending electrical energy in a form of voltage and current. Okay? So it's sending cable from here to here to this building. Okay? Is it possible to send the electrical energy using single cable? No. No, there must be voltage difference. Yeah? So they use two cables, a parallel cable, and they are sending voltage signal. Yeah? When they do this, they are sending voltage difference between these two as a very large volt. Yeah? Because they have to send it through long distance. But what's important is they ground it. So they connect this part to here. So in the circuit, they use this kind of symbol. So that's ground. So when we receive voltage here, when we receive voltage this part, this side is also grounded. Okay? So if we measure the voltage using multimeter, between hot and ground here in this receptacle, we are measuring 220 volt, right? So this point is 220 volt higher than this point, and this point is grounded. Why they use ground as a common voltage reference point from power plant to the university or house? Why they use ground as a common voltage reference point for power plant, factory, university, house, apartment, everywhere? Why?
Ground is everywhere.
Ground is everywhere.
Yeah.
Because this is the earth. We are living on the earth. Yeah? So we have to send voltage signal from here to there, all over the world. So there must be one common voltage reference point. Yeah? When you say voltage is 220 volt here, then with respect to what? Ground. Yeah? We need a common ground. That's why earth is used for ground or voltage reference point. Okay? That's ground. And that is the earth in the circuit. Okay? When we make medical device, or battery operated device like a smartphone or health band or something like that, are they grounded or not? Yeah, we have a smartphone here. I'm holding it. Yeah? Is this grounded or not? It is not grounded. Where is the connection? No, it is not grounded. Yeah? It is not grounded. But it's working perfectly fine. So what's happening?
You say that in this case you are not ground, but when you touch the window, you are ground.
Yeah.
But it is the same case. You are totally ground. You are the same.
So that has nothing to do with the device. Okay. Now we have a device. This is a device. Okay. It has a display. It has a wireless communication, and now it even has a electrode connected to the body. Yeah? And this device is being operated by a battery. Okay? So if I hold smartphone or health band, my body is not grounded. device is not grounded, yeah? My body and device all together are floating, which means I'm not grounded. Is it okay? Is there any problem of being not grounded?
You have to choose reference link.
No, it's
Inside battery is
Okay, so what's happening is, we are going to measure voltage between these 2 points. Okay? Okay. And we are going to do A to D and microprocessor and display voltage difference between these 2 points. Okay? So, this voltage is 1 millivolt. This voltage is 0.9 millivolt. When you say this voltage is 1 millivolt and this voltage is 0.9 millivolt, we have to specify reference point, right? Since this body is not grounded, I'm just arbitrarily choose this point as the reference point. So what I'm saying is, this point is 1 millivolt with respect to this point. This point is 0.9 millivolt with respect to this point. Okay? And this point and ground are not connected. Okay? Then what's the voltage difference between these 2 points? 0.1 millivolt. Is there any problem with that? No. There is no problem with that. This is perfectly fine. This is perfectly fine. In this situation, if I ask you to find out the voltage between ground and here, how much is the voltage? Nobody knows. Nobody knows, nobody cares. Yeah? Doesn't matter. Why do you want to know the voltage between this point and this point? Doesn't matter. So everything is happening in this system. Okay? So we are going to design a circuit. Okay? So here we are going to have a power supply, battery. Right? So this battery is 3 volt and it's going to provide voltage over there. And this point is going to be connected to here. Okay? And within this system, everything connected to this line is regarded as 0 volt. And all the voltage on all other points will be measured with respect to this point. So this is circuit voltage reference. Some people call it ground. But this is not real ground. This is circuit voltage reference point. Real ground is this ground. Okay? But we usually call this ground. Okay? So don't be confused. Okay? Even though we call it ground, this means this is a circuit reference point. Reference voltage point. Real physical ground is really this ground. Okay? In some device, like refrigerator, TV, or big electric machine, they connect this thing to here. Okay? Then the device itself is grounded device. Okay? In that case, circuit reference point and real ground are the same point. Okay? Okay? But in mobile device or in many medical device, we do not connect circuit reference point to the ground. They are separated. So this kind of device is called isolated device or floating device. All mobile devices are floating devices. Okay? So back to your question. How do you connect body to the ground? We just put any electrode on any part of the body and then connect that electrode to circuit voltage reference point. That's it. Then This point and circuit reference point, those points are going to be voltage reference point with equipotential surface, yeah? With zero, supposed to be 0 volt. Yeah? But if you really measure the voltage between real ground and this circuit voltage reference point, then the voltage difference between these 2 points could be 100 volt. Who knows? Nobody knows. Okay?
What
Okay.
about the battery you talked about? If you add a battery,
Yeah?
you said 3 volts. That will be in reference to ground.
Okay.
And then you connect to the body, which is
So
not.
that's also very common question. You can buy 1.5 battery from the store, right? You can find the multimeter.
It's from the.
You can find the multimeter. And you measure voltage between these points. This is reference. Okay? What's going to be the voltage readout? 1.5 volt. Okay? 1.5 volt. If I connect 1.5 volt and 1.5 volt, 2 of them in series, yeah? I measure voltage like this. What's going to be voltage? 3 volt. What's going to be the voltage? 1.5 volt. What's going to be the voltage? Minus 1.5 volt. Because I am using this as a reference, voltage reference. So this point is 1.5 volt lower than this one. Yeah? So I put my reference here and I measure voltage here. What's going to be the voltage? 1.5 volt. If I measure voltage down here, minus 1.5 volt. If I change reference point here, this is 1.5 volt, this is 3 volt. Okay? So choice of voltage reference point is arbitrary. Once you choose it, that's the setting. Okay? If I connect this thing to Earth's ground, then I measure it 1.5 volt minus 1.5 volt. The only difference is this point is connected to the ground. That doesn't change anything. Okay? Okay? So this is very common question and in some sense confusion. Okay. So that's all about ground and earth. Any other question? No? Okay. So are you okay with the lead field and biopotential measurement and impedance measurement? All of those? Okay. You have to always think about 2 vectors. One is a lead field vector, the other one is source or injected current density. Okay. And try to find the direction and magnitude of those vectors. Okay? Okay. You know, when I draw circle and I said we have 2 electrodes and I'm injecting current here, then I said that there's going to be current like this. Yeah? How do I know this? How do you find this? How do you find the current flow? How do you find this current flow? To be able to find this current flow, you need to solve what? This equation. Laplace equation or Poisson equation. You remember? We spent a lot of time to understand what is Poisson equation, what is Laplace equation, and how to solve it. In order to find out this kind of lead field, current density distribution or voltage distribution and so on, you should be able to solve this partial differential. In most cases, numerically. How do you numerically solve it? You use COMSOL or some numerical analysis software. Okay. So this is something you have to remember also. Yeah. I can easily draw this. Yeah. But that's not really easy thing to do. Actually. Yeah. Okay. So let's come back to this screen. I hope now you can understand in a much better way. I'm repeating this many times. Yeah? So I'm going to show you this thing. So what is this? This is the homogeneous rectangular domain where we have dipole at the center. Okay? And I want to find out what's going to be the current density and what's going to be the equipotential line. Okay? To find out each field distribution, I have to solve this equation, Poisson equation, numerically, with boundary condition. And what's going to be the boundary condition for this case? Outside the domain is just the air, insulator. So we have to use Neumann boundary condition, which means Neumann data is 0 everywhere. Okay? Then we can easily find the current flow this way, yeah? And solid lines are equipotential. Is this current flow, white line, are they lead field or are they, what are they?
Moment.
They are not lead field. These white lines, they are not lead field. What is a lead field? Lead field is always related to what? Voltage measurement, right? So we have this dipole. This is the dipole, right? No, this is the dipole. Yeah? So we have equivalent dipole at the center. Right?
Yeah.
Okay. Now, I want to measure voltage between here and here, between these two equipotential lines. Then we will be measuring voltage difference between this equipotential line and this equipotential line. Right? And that voltage difference can be predicted by the inner product of lead vector and this current source vector. How do you find the lead vector in this case? We have to solve this equation again using injection current here and here, right? And that will give us this kind of injection, right? And then we are going to have a lead vector blown here, and this vector and this vector should be multiplied as the inner product. That will give us voltage, right? So in this figure, I'm showing equivalent dipole, okay? And these white lines, they are not lead field. They are return current. They are return current. Remember? There are, without injecting any current outside, from outside, there are two kinds of current inside. One is impressed current, the current produced by the neuronal activity cell, which is the dipole. Yeah? Because this dipole exists as a source, there's going to be current everywhere. That was the return current. What was the return current? Minus sigma gradient of time. This was the return current, right? These white lines are return current. These are not lead field. Okay? So I'm confusing you. There are several things existing here. Yeah? In bioelectricity, there are several things. Yeah? And you should be able to distinguish all of those terms clearly. So I'm repeating the same thing over and over. Yeah? When dipole moves, field change. like this and like this. If conductivity change, then field change. Okay? Okay, so you can understand the triangle over there in a better way, right? Yeah? So this is lead 1, lead 2, lead 3. They form a triangle, and each of them define one lead vector. Yeah? When you have internal dipole moment, as I am here, as a cardiac vector, yeah? Then basically you find the projection of this vector on this line, and that line. That's same as taking the inner product with that vector, and the lead 1 is a horizontal vector. Lead vector is horizontal one. So we have different things. We can say the same thing about. And now this is all about the impedance measurement. In this case, we are injecting current from device we made. Okay? And then we are interested in finding only the current density distribution we produce. So for example, if you attach one electrode over the red one and green electrode down there, now let's think about, we are going to measure voltage between those two electrodes. Okay? Then this is the lead field map on the surface of the brain. This is the current density when we inject current from red electrode to green electrode. And this is the current density, which means if we are going to measure voltage between red and green electrode, then this is going to be lead field map, magnitude of lead field map, because we calculate the current density due to injection current between red electrode and green. Okay, so in real situation, lead field map is quite complicated in many. Okay. Now let's do a little bit of mathematics. So this is some other issue. Now we want to find out resistance. Okay. So you want to measure resistance between spherical electrode with semi-spherical electrode. So this is half of a sphere, metal or conductor, with radius of A. And now you are injecting current from here to here, okay? And then this is the ground, real ground, okay? And you connected this to ground point very far away. Or this is the sea, Pacific Ocean. Okay? You want to measure the resistance of the Pacific Ocean. Okay? So you prepared electrode, half sphere with radius of A, okay? And you inserted this electrode to the Pacific Ocean, okay? Like this, and then you inserted this reference electrode to the Pacific Ocean, but at the position far away. Okay? So basically, you are injecting current from here to the reference point far away. Can you understand the setting? Okay? Then how current will flow? Think about it. So in this case, all the current will enter, yeah, and then current will escape from the surface of this electrode, right? And the conductivity of the water in the Pacific Ocean is sigma. So everywhere conductivity is sigma. And this is sphere. Is there any reason why current will flow more toward certain direction? Is there any reason why current will flow more vertically rather than horizontally? Is there any reason? There is no reason. Yeah? There is no reason for any directional preference. So current will escape very uniformly through all directions. There is no concentration of current in this case because it's sphere. Yeah? Now I want to find out what kind of voltage is going to be measured over there. If we know voltage and if we know this current, yeah, then we can divide the voltage by the current, and this will give you what? Resistance of the Pacific Ocean. Electrical resistance of the Pacific Ocean. Okay? What do you think? Is this strange or not? Is it good? Yeah? Yeah. So how do you solve this problem? We are dealing with this equation. We are dealing with this equation. So I'm trying to provide some example to solve that partial differential equation analytically. There are several cases where we can solve this equation analytically. If we solve this equation analytically, then we find current density inside, right? Yeah. So I'm trying to give you some simple example. If this example is too difficult, then let's start with this one. Let's think about a cylinder, perfect cylinder. Inside the cylinder, there's just a homogeneous conductivity material, sigma, conductivity sigma. And we attach the large electrode at the top and another electrode at the bottom. Okay? And then we apply. So this is voltage reference here. So bottom electrode is grounded. Not really grounded, but treated as a ground point or voltage reference point. And we applied V0 volt to the top electrode. Okay? Now I want you to find out current density distribution, voltage distribution inside this cylinder. How do you find it? This is my body. I moved my head and I pushed my leg. So my body is like this. So I attach one electrode here and another electrode here. And I'm going to measure voltage between these 2 points due to some equivalent dipole inside. Then what should I do? I should find lead field map. How do I find lead field map? I inject current and I need to find out current density vector inside. Yeah? Okay? Then I have to solve this equation. Yeah? And this is the example. Instead of injecting current, I just applied constant voltage at the top part. Okay? So I need to solve this equation in this domain. And outside is L. How do I solve it? conductivity is constant, right? So this can be moved in front, right? And this moved in front, then this can be divided. I'll do this here. So I'm using symbol of U here for the voltage. So I need to solve this equation, right? Sigma is constant, so I can do this. Right? I can move this thing to the front. And I can divide it. Divergence gradient, that's Laplacian. So I just need to solve this equation. Laplacian equation.
Boundary condition.
With boundary condition, which is common. What is the Laplace equation? I'm using U. This is Laplace equation. From the symmetry of the problem, is there going to be any change in voltage along x and y direction? No, there is no voltage change along x and y direction because everything is changing along z direction only in this case. So this is 0. This is 0. From the geometry of the problem itself. How you are sure? I'm sorry, I cannot explain more about this. Yeah, you just understand this by yourself. Yeah? Then we have this problem. So what is the solution? As a function of z, what is the solution? K1g plus K2. How do you find it? You just do integration. Yeah? High school mathematics. Yeah? You just do integration. Then, you integrate this once, then what do you have? Round U, round G, dash K1. And you integrate again. Then U is this thing. Yeah? Okay? Then what kind of boundary condition you have? U, Z equals 0, that is what? K2. Yeah? And what's the value at Z equals 0? Voltage is 0. Yeah? From the boundary condition. So this is 0. And at U equals G, G equals L. K1 L. Yeah? K2 is 0. What is the value of this thing? V is 0. This is given value. So what is K1? L over V0 over L. Right? So what is U Z? Voltage as a function of distance G. V0 over L times Z. Clear? Okay. Good. Very good. Very good. Very good. So this is the voltage. So what is the voltage at the bottom? 0. And the voltage increase as we move up linearly. And when we arrive at the top, at Z equal L, the voltage is going to be V0. Okay? So if I draw, this is Z, yeah? This is G equals 0. If I draw voltage U, voltage must start from 0. Right? At the bottom, voltage 0 volt. And at this point, L, what is the voltage? V0. At this point. Yeah? V0. Then between these two, voltage should increase linearly. This is the solution. This is the solution. Okay? So voltage increase linearly as you move up. Now, what is current density? What is current density inside here? So current will flow from the top to the bottom, right? So what's going to be the current density as a function of G? This is minus conductivity times gradient of U. We calculate the gradient of voltage, that will give you electric field, right? And you multiply conductivity, then that's current density. Right? What is this? Minus sigma. What is the gradient of this thing? If we take the derivative of this thing with respect to x, that's 0. With respect to y, that's 0. With respect to z, that will give us what? V0 over L. And then what should we put here? Unit vector along z direction. Or k. Yeah? Because gradient makes vector from scalar value. Right? This is it. So what's the direction of current density? Minus AZ direction. Which means from the top to the bottom. So current flow from the top surface to bottom surface. Because the direction is minus AZ. Current flow down. Okay?
Yeah.
Is there going to be any change in current density depending on Z? Is this constant or change with Z? Constant. It's constant. So no matter where we are, current is constant. Constant current density produced inside the cylinder. That makes sense, right? That makes sense. Then what's going to be the total current? Total current
by S.
is magnitude of this thing, sigma V0 over L, magnitude of the current density, multiplied by what?
Area.
Surface area. This is total current. Easy. Agree? Yeah. Then what is going to be the resistance? What's going to be the resistance between top and bottom? Voltage divided by current. What is the voltage? V0. Because the voltage plus. What is this? This is 1 over sigma L over S. Very famous equation, right? You didn't like it. I think some of you will like it. Okay, so you can theoretically and very rigorously derive this formula, which is very famous, right? From Laplace equation. And the other thing is, lead field, if we measure voltage between top surface and bottom surface, in this case, lead field is constant throughout the region. Lead field is perfectly constant in this case. Because everywhere we have this kind of lead field. Yeah? So no matter where we have internal current source, doesn't matter. We are going to measure the same voltage. Let's say this is that segment, and we are looking at cross section, and current density is uniform everywhere, as you derived here. Yeah? Current density is uniform everywhere along this direction. So current density at this point, current density at this point, current density at this point, or this point, this point, this point, this point, everywhere, current density vector are same. Which means if we are going to measure voltage between these 2 points, which is produced by the heart located here, yeah? The voltage we measure between this point from the dipole at this position or the dipole at this position, they are going to be same as long as the source dipole has the same directional measure. So in this case, any point inside had the same sensitivity. Right? Yeah. Because it produced uniform current. So if you are going to, you don't know where you have internal source. Okay? You don't know where you have internal source. Then what's going to be the best electrode configuration? The electrode configuration which will produce uniform lead field. That's going to be the best one. How do you produce uniform lead field? You can do that when your body is a cylinder and your body has just single conductivity. Then you can produce uniform lead field. Otherwise, it's not possible. But you can always think about this kind of case. If you are facing a situation where you don't know the position of the source, okay? But you want to find out certain electrode configuration which will give you always the largest signal. Even though the dipole position change, move around, yeah? Then you should try to produce electrode configuration which will produce uniform lead field. Okay? Usually that's impossible, but you can try. Okay? Or you can try to find some configuration which is very similar to that kind of uniform lead field. Okay? Okay. So it has very intuitive meaning here. Eh? It's nice to have, it's nice to confirm this formula, very famous formula, but in addition to that, it has very good intuitive meaning here. Yeah? Okay. So you should remember uniform lead field distribution is sometimes very desirable. Okay? Okay? But it's impossible to achieve that. So whenever you need that kind of thing, you should find something which is very close to this kind of case. Okay, now let's go back to this example. I hope we are finding it a little bit easier now. So I'm going to forget about Pacific Ocean. Eh? That's no good. That's no good. You want to develop a device which measures conductivity. There's conductivity meter. People use it in chemistry and biology. They use conductivity meter. And now you're developing conductivity meter. Yeah? And this will give you one idea about how to make conductivity meter. So in some sense, you prepare a container, cylindrical container again, and you fill this container with a solution of a conductivity signal. Okay? Now you want to measure conductivity of signal in a very simple way. What you can do is you install large electrode at the bottom, large electrode at the bottom, and then you put electrode of half sphere, okay? Small one, and then you inject current between these two and measure voltage between these two. Some of you might be wondering what's happening about the contact impedance. We'll ignore the effect of contact impedance for this simple problem. Huh? So this is the setting here. And we are assuming that this A, radius of the semi-sphere, is very small compared to the diameter of this container. So this is very small. So we are assuming that this space is very large compared with the diameter of the sphere. Surprisingly, the resistance between this semi-sphere electrode and large bottom electrode, the resistance between these two, how they find the resistance between these two? We assume voltage here is 0, yeah? And we assume voltage on the surface of the half sphere is V0, just like before. Yeah? And we solve this equation in spherical coordinate system. Here we use the Cartesian coordinate system, but because this is a sphere, we better use spherical coordinate system, which you don't like. Yeah? We have to use spherical coordinate system to solve this problem. Yeah? And then we repeat the same process again. And we find voltage, and then we find current density as the gradient of voltage multiplied by conductivity, and then we find total current by calculating the surface integral of the current density, and then we calculate voltage divided by that total current. Then we have resistance. Surprisingly, resistance is this value. 1/2 pi A sigma. Strange. What is strange here? Sigma appear here, okay? And A appear here. If A is getting smaller and smaller, then resistance is going to be increasing. So if you use a small electrode here, then measured resistance is going to be bigger. So the resistance depends on the size of the electrode. If this is getting smaller and smaller, then this size is much bigger than radius, right? So this approximation is better, okay? So this approximation is more accurate when A is small, okay? Under that case, the resistance, the total resistance is determined by A and sigma. A and sigma. Size of this container doesn't matter. Why? So you can use this method to measure the conductivity of the Pacific Ocean. I was not joking. In the answer, there is no parameter about size of the ocean or depth of the ocean. What are the results? There are two things. Diameter of the electrode, conductivity of the ocean. This is good. Why? And why? Why we have this kind of result? Here we are assuming that size of the electrode is much smaller than ocean. Why? Why the final result only include the parameter A, which is the diameter of the electrode? Think about it. think about the lead field again. So we have tiny electrodes like this. Okay. How current will flow? Current will flow radially all over. All over. Okay. So current will flow radially all over. Right after short distance, the current density is going to be very small. So current density decreases very rapidly. Why? Because think about half sphere with radius of A. How much surface area it will have? 4 pi A squared divided by 2, because it's a half sphere. Right? If injected total current is I, then right at the surface of this electrode, the current density was 2 pi small a squared, right? Right? And A is very small. Yeah? And if this A, large A is getting bigger, this same amount of current must be spreading all over. Yeah? And right after short distance, current density everywhere is going to be almost zero. Because it spread all over the Pacific Ocean. So even though conductivity down here is very much different from conductivity near here. Let's say conductivity near this electrode was sigma. Conductivity down here was 1000 sigma. Doesn't matter. It doesn't matter. Because the current flowing here is so small, there is no sensitivity. This means if electrode is small, current density near the electrode is big, and right after that small electrode surface, current density rapidly decreases. So anything happen, little bit away from the electrode, doesn't matter. Because it has such a small sensitivity. So if you use a small electrode to measure something, you can see only small area. Agree? Okay. So you have nearsighted. If you use a small electrode, you cannot see far away. Because when you inject current through that small electrode, you have very high current density right near the electrode, and then it spread all over, and you have quickly very small current density. This is away from that small electrode. So you are measuring bioimpedance using needle electrode. Using needle electrode. So this is tissue, and you inserted needle electrode one, another one here, and this is electrode. And you are passing current between here and here, and you are measuring bioimpedance. You think we are measuring impedance between this, the area between these two. Is that true? No. You are measuring impedance of the tissue right here and here. Okay? You are not seeing anything in the middle. Because the current density around this area is much, much higher than the current density around this area. So this impedance measurement has very small sensitivity to the tissue down here. If you want to measure impedance of this area, what should you do? You have to use a large electron so that you have what? More or less uniform current density. Then you have sensitivity. Otherwise, you don't have sensitivity. is a good example to understand the kind of phenomenon. So it's also important to think about size of the electron in addition to the position of the electron. How do you solve it? We have to use a spherical coordinate system. So we have Laplace equation, yeah? And you find expanded form of Laplace equation for the spherical coordinate system, and then you notice that there's going to be no change in voltage along any angular direction. Okay? So there's going to be change in voltage along only radial direction in spherical coordinate system in this geometry. So we have only the variable r, okay? And that's the form of Laplace equation for the spherical coordinate system when potential change only along the direction of the variable r. Okay? And we solve that equation. How do you solve it? You integrate twice. You integrate twice, and then you apply these two boundary conditions. Okay? And then you will find this kind of voltage. So voltage here is V0, and then as you move away along any radial direction, voltage drops at 1 over r. Okay? 1 over r. If you move 10 meter, then voltage 1 over 10. 100 meter, 1 over 100. Something like that. How do you calculate current density? This is the voltage. So to calculate the current density, what should you do? You calculate the gradient of voltage. Okay? So we calculate the gradient of this thing. So we take the derivative of this thing with respect to r. This is 1 over r. So derivative of 1 over r is going to be 1 over r squared. So current density will decrease even more quickly as 1 over r squared. So if we move a little bit away from the surface of the electrode, then the current density is very small, as you can see here. And what's going to be the total current? How do you calculate the total current? So when we know radius r, we know the current density on the surface of this large sphere. Then how do you calculate the total current? You just multiply that average current density on this surface by the surface area of the half sphere. What's the surface area of the half sphere? 2 pi r squared. Okay? And this is the current density on that surface. Then we have this much of current. This is the total current. How do you find the resistance? Voltage V0 divided by this thing. So we have this resistance. And as you can see, the resistance is determined by the conductivity of the positive ocean or the container and radius of the electron. So if you use very small electron on a large amount of liquid, then by just using that small half sphere sphere edge electrode and use a large return electrode, then you can easily find the conductivity of the solution because of this. And another thing is, from here, current spread all over, yeah? And right near the electrode, this current density streamlines are very crowded, meaning that there's high current density. So everything, anything happening around here contribute a lot to the measurement. But anything down here, they don't contribute because the sensitivity is so small. In other words, current density is so small, or the lead vector is so small. So if you want to see large area, you have to use electrode with large size. Yeah? There is no other way. Yeah? There is no other way. if you try to measure large area using small electrode, it's like trying to invent a time machine. It's against the physical law. Okay. This is a little bit modified question. When you have one electrode like this one and another electrode as a half sphere down here, what's the resistance? Then you can do a little bit more of mathematics. Then you can find this kind of formula. It will be interesting to see whether you can draw current density for this kind of configuration in Newton. Then you can solve this equation and you can draw current density line. What's going to be the current density line in this case? Think about it. So already think about this case, uniform sensitivity and very non-uniform sensitivity. High sensitivity near the electrode and almost zero sensitivity in the region away from the electrode. When electrode is small. Okay. Okay. Any question? Anybody can explain the meaning of that and meaning of this? Here we are using just the two electrodes to measure impedance. So we are injecting current between those two electrodes and measuring voltage between the same two electrodes. In this case, lead field map and the induced current density map are same, right? So every point inside, you are calculating inner product of lead vector with the same vector, right? So the value is going to be maximum. Okay? So if you measure impedance of a body using two electrodes, inject current and measure voltage on the same pair of electrodes, then you are measuring the maximum impedance. Okay? Now, we are injecting current using these two electrodes and measuring voltage using these two electrodes. Then what's going to be happening is dotted lines are lead field, right? This is the lead field. This is the current density which we'll have when we inject current from here to here, right? So dotted line, those are lead field. Solid line, that's the induced current density. So inner product between those two current density distributions will give us measured voltage here, right? At this point, we have positive sensitivity, even though their angle is not zero. Yeah? At this point, we have negative sensitivity. So if we calculate the impedance as voltage divided by current, the impedance we get from this configuration is going to be always smaller than that configuration. And if conductivity of this region increase, then impedance decrease. In other words, voltage decrease. But if conductivity of this region increase, then impedance increase. This voltage increase because it has negative sensitivity. So we have a confusion in this case. In this case, we have only positive sensitivity everywhere, okay? And maximum sensitivity in some sense everywhere. Okay? So there is no confusion for that case. Is this bad or not? In some sense, this is bad. Okay? If you don't know the sensitivity distribution, then this is bad because you don't know how to handle it. If you don't know which part has positive sensitivity, which part has negative sensitivity, if you don't know that kind of sensitivity map, then there's no way you can interpret the measured data from this case. Okay? If you want to correctly interpret the data from this case, then you should know sensitivity map. Where you have positive sensitivity, where you have negative sensitivity, you should know all of those. Then, this is okay or not, because you know sensitivity map. Then you can properly interpret the data. Okay. This is the cloud of sensitivity. And here's something which I want to show you. So this is my hand. This is my hand, and I'm attaching one electrode up here, and another electrode down here. And I'm injecting current from here to here. Then at the middle, I'm going to have more or less uniform current. Okay? So my current density is more or less uniform. Now I'm going to measure voltage on the surface of my arm. So I'm putting one pair of electrode with a small gap. And I'm putting another pair of electrode with large gap. Okay? And I want to find out lead field of this electrode configuration and this electrode configuration. When we have a pair of electrodes with small gap, how do you find the lead field? We inject current from here to there, right? Yeah. When they are close, is there going to be current down here or not? There's going to be not much current down here. If there's blood vessel down here and changing conductivity, using that kind of electrode, will it be able to see it or not? We cannot see it because we don't have sensitivity down here. Because the lead field map gives us there's significant lead vector only surface area. Yeah? So if you want to see something at the deeper position, what should you do? You have to use electrode with large gap. Then that electrode pair will produce this kind of lead field, which will give us somewhat measurable amount of current density down here. Question?
Also in this configuration, the lead field direction at many points will be parallel to the...
Yes. Parallel. So we are going to have good sensitivity. Yeah. There's going to be negative sensitivity area actually. If we inject current from here to here, then actually there's going to be some current passing through this way and then come back to this way. But as we move away this part, the amplitude of the current density flowing this direction is going to be very small here. So by controlling the distance between electrodes, you can change the depth of your view, how deep you can see. Okay? Okay. If you keep the gap same and only change the size of the electrode, then there's not much effect. If you keep the gap same but change the size of the electrode, then read field are almost same. So if you want to change the depth of your view, what you have to do is you have to really change the size of the gap of the electrode. Okay. So, there are many things we can think about. Okay? There are many things you can think about. Given certain case, how you are going to design electrode configuration, then you have to think, and then you should analyze the lead field carefully. Then you can come up with probably not the best, but a very good electrode configuration for your application, which will improve the performance of your signal, sometimes very significantly. So without knowing this kind of lead field concept, sometimes you come up with a design which is basically nonsense. Okay? And you don't know why. You don't know why I don't have signal. Okay. Any questions? Any question? But next week we are going to have a midterm and time of the question. I already gave you one problem.
Yeah.
What was that? I forgot.
The ocean.
Yeah? Oh, electrode placement for the best measurement of impedance change in the wrist, right? Yeah. That was that's going to be one question. Something like that. Yeah? Something like that.
I mean, there is no calculation, something like this, equations.
Well, there might be some equation, but not many. Yeah? Yeah. I don't ask you to prove anything. But you can prepare one sheet, A4 sheet, both sides, yeah? With a very fine pen, if you like. Any other question?